Why is our galaxy called the Milky Way?
That's a very good question. I tell you, there's something even more profound to it, because there's many different cultures who've never been able to speak to each other, call the Milky Way in their own language. So we're now in Leeds. It's very difficult to probably see it, but if you go to a dark night, a clear night out in the open, you can see a white band across the night sky, and it looks almost like it's milky. And it's not a Milky Way, what people thought, but it's the billions of stars that our Milky Way is consisting of.
How old is the Milky Way? And are there other galaxies in the universe that are possibly older?
The latest that people have been able to get ages. It's actually very difficult, on the one hand, to get the ages of a Milky Way, and on the other hand, it's perhaps a little bit easy. But what people have found is some very old stars in our Milky Way, and the ages that they have found for that are about 10 to 11 billion years. So if the stars in the Milky Way are 10 to 11 billion years, then the Milky Way itself will be around 11 billion years as well. So that's the age of the stars. But what people now think is that the first galaxies, the first Milky Ways, were actually formed pretty quick after the Big Bang. So what people now think is that the oldest galaxies are about 12.5 billion years old.
Are old galaxies quasars, maybe?
That's an interesting one. Let me just say what we think a quasar is. A quasar is really very bright, and the first time that people saw a quasar, they saw a very bright star-like object, but it was very far away. And because it looked like a star, they said it's like a quasi-star. Let's call it quasar. And then these people from the watches actually called their watches quasars and pulsars. But these quasars we now think are powered by supermassive black holes in the center. These are black holes, and people know that if you've got a black hole, nothing can escape. But if something falls into it, it will smash into it with a very, very high velocity and energy, and that energy is being radiated, and that's how we can see these quasars.
So if a quasar is so far away, how do we actually see them and know they exist?
Because they're so incredibly bright. It's amazing when you think about brightnesses, because I think that our sun is pretty bright. I wouldn't want to be able to walk on the surface of the sun. We would be toast, wouldn't we? But such a quasar can be as bright as 1,000 billion times the sun. So it's so bright that you can see it from the furthest reaches of space.
How big is our Milky Way? What is our physical location within it?
Well, the Milky Way contains about 100 billion stars. Our nearest neighbor is a few light years away. So you can well imagine, if you want to fit 100 billion stars in a volume of space, and the average space between them is about a light year or so, then it's pretty big. And I think the latest numbers that we have for the size of a Milky Way, it looks like a frisbee with some spiral waves in it. End to end, it will be about 100,000 light years. So it will take light 100,000 years to go from one end to the other end.
So if light takes 100,000 years to cross the Milky Way, how long would it take us to maybe travel to the other side of the Milky Way?
The latest estimates that I read about interstellar travel, just going to the next star, I think people were budgeting for thousands of years already. If that's for 1 or 2 light years, then you can multiply it yourself.
So have we ever sent anything into the Milky Way? And do we actually have any images of it?
Well, people have been sending space probes since several decades now into the solar system. And I believe it was in the 70s that there were 2 probes were sent to the edges of our own solar system called the Voyagers. And one of them has just recently left the solar system and is actually now moving at thousands of kilometers per second into interstellar space, into the galaxy. It's got a little bit of a message for aliens as well, telling them everything about us until 1970 something.
Are all galaxies the same shape as ours?
No, these galaxies come in many shapes and forms. I'd want to put something into perspective for you. You may have heard of the Hubble Space Telescope, and at some point they decided to have that telescope look at the same part of the sky for a very, very, very long time, just to look at the faintest structures they could find. And they looked at the patch of the sky that was, I think, 1/10 of the size of the full moon. And to give you an idea, if you stretch your arm, then your thumb will be as large as the moon. And then divide that by a factor of 10, and you know how small a part of the sky I'm talking about. They found 10,000 galaxies in that small bit alone. And what they found were galaxies that look like the Milky Way, look like the frisbee with spiral waves in it. We call it the spiral galaxy. Other galaxies look like rugby balls. They call them elliptical galaxies, just basically shapeless. And other ones had a very interesting name. They are called irregular galaxies because they looked irregular.
You talked about the shape of our Milky Way, but how is it possible to know the shape of the Milky Way without any actual images of it?
Indeed, because if you're sitting inside the Milky Way, it's very hard to actually move out and make a picture. Let's imagine that we are having a frisbee in our hands and we live somewhere inside that frisbee. Now, where we live, I think we're about a third way out, a very quiet suburban area in the Milky Way. And if you just position yourself in that frisbee, if you look up, you don't see a Milky Way. If you look down, you don't see a Milky Way. But if you look sideways, you will see this Milky Way, this band of stars. There's some tricks that we can do. We can determine distances to various structures in the galaxy. And what we found was that there was a recurrent pattern. There were spiral waves inside this frisbee. So it's not a smooth galaxy, but there's different patterns there that we can identify with the spiral arms that we find in other galaxies as well.
So do we have maps of all the stars in our Milky Way?
We have many maps of stars, and I tell you, there's a revolution going on as we speak, because I just mentioned that we determine distances, but it's not very easy to determine distances to stars. But at the moment, there's a satellite in space, a European satellite called Gaia, which is measuring distances to more than 1 billion stars.
So we've spoken a lot about stars in the Milky Way, but is there anything other than stars?
That's a very good question. Yeah, we've got these billions of stars, but what people have found is that galaxies are actually more massive than what we would actually assume if I would add up all the masses of all these individual stars. Part of it is there's a lot of gas and dust in between the stars. We call that interstellar matter. But it turns out if you add up everything, that's slightly less or less than the stars. But it turns out that galaxies are probably 5 to 10 times more massive than if I add up all the gas, all the dust and all the stars. And that's what we call dark matter. A, it's called dark because we can't see it. B, it's called dark because we don't know what it is. And C, it's called dark because it just stretches the imagination, I guess.
But how can you really justify dark matter? Is it just our galaxy or is it seen all over space?
The dark matter was originally discovered in other galaxies because it's often easier to study a galaxy from outside. It turns out that every galaxy that people have looked at are more massive than we would infer from the stars alone. Then people found that clusters of galaxies are even more massive than what you would infer from all these galaxies with dark matter. And now local studies of our own galaxy have indicated that our own galaxy is more massive as well than we would assume based on the stars alone.
Are there other Earth-like planets in our galaxy, or do we think we're unique in our position and our composition?
Yeah, I take it that you ask about Earth-like planets because you're after alien life, aren't you? And you expect it to be on planets that are like the Earth, and that's a fair comment. In a way, we don't know how alien life would look like, but let's just take Occam's razor. When we think about alien life, okay, let's look at what we know best, and that's life on our own planet. Why do we have life on our own planet? Because we've got nice liquid water. It's a rocky planet. We don't sink to the bottom just like would happen if we would be on Jupiter. We've got all the nice oxygen, etc. So what you want to look at are planets that are like Earth. But it's very difficult to find them. So we have, in the last 20 years, so far discovered about 2,000 planets on other stars, but most of these planets are very big and very massive, because you can well imagine that the more massive a planet is, the easier it is to find it. So we know of a lot of other planets, and the numbers will be billions if you just extrapolate everything we know. We expect to have billions of these huge planets around. But after 20 years, the first one was 20 years ago, our methods are a little bit better. The methods are smarter, the technology is better, and we're getting there. We are now, a couple of Earth-like planets have been discovered in the last 1 year or so. So they are there, and if we extrapolate based on just a few detections, the chances are that we even have more Earth-like planets than these huge planets around other stars. So possibly billions of Earth-like planets in our own galaxy.
You said before that the galaxy is about 11 billion years old. So I was wondering if new stars are still being formed in the Milky Way.
It's pretty well proven now. We can form stars from these interstellar dust and gas. If I would have a collection of interstellar gas and dust, all these particles could at some point attract each other, and such a cloud of gas could shrink and become smaller, and would become denser, and if you compress a gas it actually becomes hotter, and at some point the gas would be compressed so much that a new star would be born. Turns out, when people look at the history of our own Milky Way, 10, 11 billion years ago there was much more gas and dust, and a lot of stars were formed at once. Well, we still look at these stars now. Our own sun is from the third generation of stars, if you like. It's about 4 or 5 billion years old. But we've got much less gas and dust available now, but still stars are being formed, just at a lower pace than in the past.
So what I'd like to know about the galaxy is, well, if the Earth orbits the Sun, what is the Sun orbiting to stop it from crashing into other stars?
It's almost exactly the same thing. The Earth is orbiting the Sun because of the gravitational attraction of the Sun, but it can't fall into the Sun because it's just moving in circles. And the Sun itself is moving around the center of our galaxy. One orbit of the Sun around the center of the galaxy is about 200 million years. So the last time our own Sun was at the same position as it is now, dinosaurs were walking around on Earth.
What is it actually orbiting then?
Yeah, it's an easy answer to say it's the center of the galaxy, but if I now zoom into the center of the galaxy, what we find is a very massive body. We found that there must be something that's smaller than the size of our own solar system that weighs about 1 million times the mass of our own sun. That's in the center of our galaxy. And it looks like it's a black hole, a supermassive black hole.
What's stopping the Milky Way from falling into other galaxies through this gravitational attraction we talked about?
I've got bad news for you. Nothing is stopping the galaxy from colliding with other galaxies. In fact, you may have heard of the Andromeda Nebula, which is a spiral galaxy just like our own galaxy. It's a couple of million light years away from us, but we are on collision course. They are moving towards us and we are moving towards them. We knew already from measurements over many years that they were moving towards each other, but there was a recent study a year ago that actually indicates that we're not only moving towards each other, we are on a ram course. We are going to hit each other in about 5 billion years from now, that we will be colliding with Andromeda.